Welcome back. Today we have text problem 12-6 for lesson 28. As always, get out a scratch piece of paper or a blank printout of the problem so you can follow along, and I'll be pausing throughout the video to give you a chance to work ahead a little bit and resume the video to see how you did. Okay, so first off, let's read our problem. And I know when I read the problem, there's a couple things I'm looking at. I'm seeing masses and distances. I'm seeing tension here. And really what I see most predominantly is the fact that our object, the scaffold, is static. So if it's static, I know I'm going to have forces acting on it. So I'm going to be bringing in Newton's second law into this. I think those are the two most important concepts to pull out of this problem. So let's go into the draw stage. This is actually a really important step for this problem since we don't have a picture. Everything that we're going to visualize in this problem is going to really depend on this step. So why don't you pause the video, do a not super detailed, but detailed enough to have the information we need for this problem. Okay, so for the draw step, I didn't even put in my D. For the draw step, we have our 60 kilogram scaffold. We have tensions in both the left and right cable. We have our window washer, a distance small l from one end, and the length of our scaffold is big L. So when we actually get into the free body diagram, those are going to be some pretty pivotal dimensions or critical dimensions as we go through all four steps. Okay, so givens, we've got our mass, the length, and the distance our 80 kilogram window washer is from one of the ends. Alright, so our next step, our assume step, it doesn't say it in here, but we have to say it. Let's assume that we are in static equilibrium. And our tasks, part A is to calculate the tension on the left side. So I'll label this left side, right side. And part B is to calculate the tension in the right cable. It says near and far. That doesn't give you a reference to which one is near and which one is far. So I'm just going to go with left and right. So long as I'm consistent, that's all that matters. Alright, so for our physics step, I want you to pause the video and write down the equations you think you will need for this problem. Alright, so how'd you do? Alright, so I listed both my Newton's second law equations. I know I'm going to need Newton's second law for something. I don't know which one I'm going to pursue. I'll probably pursue one first, and if it doesn't work, I'll go to the next. If I am going to use Newton's second law for rotation, then I need the definition of torque and the equivalent magnitude of the torque equation. Alright, so let's get into our solve step. And on this front, I want you all to draw a free body diagram for our scaffold. Now remember, we do have our individual here. We're not going to do a free body diagram for him, but he is exerting a force on the scaffold, so just keep that in mind. Alright, so I will see you in a minute. Alright, so how did you do? Well, this was a pretty involved free body diagram, so I'm going to go ahead and start from one end. Now, if we decide to pursue our Newton's second law for rotation, then we need to pick an axis of rotation. Now, as we said in our assumptions, we're in static equilibrium. Nothing's rotating, but that's okay. we can still pick an axis of rotation if it were to start rotating. Now, because Part A asks us to calculate the tension in the left cable, I'm going to put my axis of rotation on the right side. If I put it on the left side, then the tension in the left cable does not produce any torque. So I can't sum the external torque if the thing I'm looking for isn't in the Newton's second law analysis. So I put on my right side, I label all of my forces, and so I have my tension in the left cable, I have my tension in the right cable. I have the weight of the window washer on the scaffold. Notice how I have it anchored from the top, because that's where the force is being exerted. And I also have the force due to gravity of on our scaffold, and it's anchored at the center of mass of our scaffold. All right, next I set a coordinate axis, so y and x, and I said anything rotating counterclockwise is going to be positive. Now, for step 4, labeling the critical angles and dimensions, this is where picking an axis of rotation is very important. So here I have my axis of rotation on the right side. I need to have all of my critical dimensions from that point. So the distance from my axis of rotation to my scaffold weight force is L over 2, big L over 2. And the distance from my axis of rotation to the weight of the window washer is big L minus little l. And the tension in the left cable from the axis of rotation, or the distance from the axis of rotation, is L. Now if I were to change it up, i.e. part 2, my axis of rotation could be from the left side. And in that case, my distance to the axis of rotation for my window washer is just little l. For my weight force, it's big L over 2, and my tension in the right cable is just big L. So that's our free body diagram. It lists everything we need, and we can go ahead and pursue our the rest of our solve step. Alright, so let's get at it. So I'll do torque first. So Newton's second law for rotation. Now, first and foremost, the assumption we made is that we are in static equilibrium. So what is the angular acceleration of our scaffold if we're in static equilibrium? Right, it is 0. Well, that's excellent. Alright, so the sum of our external torques is equal to 0. So, you could say that. Excellent. So all of the torques acting on our scaffold will cancel each other out. Alright, I want you to pause, and I want you to do the Newton's second law for rotation analysis on our scaffold from the axis of rotation labeled on our diagram. I will see you in a few minutes. Take your time, and once you resume the video, you can see how you did. Alright, welcome back. So how'd you do? Well, we had 4 forces acting on our scaffold, but one of our torques is at the axis of rotation. So there's only 3 torques acting on our scaffold because we put our axis of rotation at the location of one of our tension forces. So, that being the case, the 3 torques I have left over, I have the torque due to the force of gravity on the center of mass of our scaffold. I have the torque caused by the window washer at a distance big L minus little l. And those are both positive because they both want to spin the scaffold at our axis of rotation counterclockwise. whereas our tension in the left cable at a distance L from the axis of rotation wants to spin our scaffold clockwise. So I have a minus sign in front of that torque. Alright, now we have the magnitude of each of our torques listed on here with the appropriate signage, and we can now convert that to magnitude and angle. And so we're left with L over 2. Alright, I don't need to talk out the whole thing, but I have converted them to magnitude and angle form. And notice that for each of my angles between my vectors, I've labeled them separately. They don't all have the same angle. Now, if we assume that this is a relatively thin slab, then the angle between our vectors is going to be 90 degrees. And if they're 90 degrees, the sine of 90 degrees is equal to 1. So that means each of my sine terms, here, here, and here, will all equal 1. So I'm left with L over 2 ms. Again, don't have to talk through the whole thing. And here we are, our result. I have my length big L. I know the mass of my scaffold. I have my length little l. I have my mass of my window washer. And again, I have L and G. So all I have to solve for, or the only thing that's unknown, is the tension in the left cable. And so I just move this to the right side of the equation and divide both of my torques here by big L. So there is my algebraic solution. And once I put in my given values, I have the tension in the left cable as 840 newtons. So that gets me through part A. I need to go to part B and find the tension in the right cable. So let's go to the next slide, and I'll copy over the free body diagram to reference it for part B. Okay, so part B, we are going to solve for the tension in the right cable. Now I'd like to change things up a little bit. Instead of doing Newton's second law for rotation, I'd like to do Newton's second law for translation. Now that we know the tension in the left cable, we're only left with one force on here that we do not know the answer for, or we don't have its value. So we're going to start with Newton's second law for translation. And again, the assumption we made is that we are in static equilibrium. So the acceleration of our scaffold is 0. So the sum of our forces acting on our scaffold are equal to 0. Okay, again, I want you to pause the video, and I want you to do a Newton's second law for translation analysis on our scaffold. Alright, so how'd you do? We have 4 forces acting on our scaffold. As we break our Newton's second law for translation into its x and y components, we see rather rapidly that the sum of the external forces in the x direction, not only is it equal to 0, but we don't have any forces in the x direction. So this is not a waste of time, but we don't need to spend any more time looking at this direction when all the action is in the y direction. So let's shift over to there. The sum of our external forces in the y direction is equal to 0. So let's sum up those forces. We have the tension in the left cable, the tension in the right cable. We have the force due to the window washer on top of the scaffold, and the force due to gravity acting on the scaffold's center of mass. And that's all equal to 0. So we need the tension in the right cable, and that's just a matter of taking our 3 other forces and sending them over to the right hand side. Well, we know the mass of our window washer, we know the acceleration due to gravity, we know the mass of our scaffold, and from part A, we know the tension in the left cable. So, as we put in all that information, we get 530 newtons. Notice that the tension in the left cable and the right cable are not equal. That's because we have our little man over here on the left side. That little man on the left side is creating a torque on the left cable, a torque that is greater on the left cable than it is the right cable. Alright, so you may be asking yourself, why didn't we do Newton's second law for translation on part A? It's so much faster, we don't have to deal with any cross products. Well, as we look at this, some of the external forces in the y direction, we didn't know the tension in the right cable or the left cable. By doing Newton's second law for rotation, we were able to take one of those unknowns out of the equation by putting our axis of rotation directly on one of our unknown forces, thereby canceling that torque completely out. In all reality, because we're in static equilibrium, I could have put my axis of rotation right in the middle. I could have put it right where the window washer was. I could have put it right here where there are no forces acting on the scaffold or anchored at that point. I can put my axis of rotation wherever it is convenient because I'm in static equilibrium. Okay, I'll let that sink in for a little bit. I've got nothing else for this problem. I will see you in class, and hopefully you have some questions for me, and I will see you then.